All right, so we're going to cover another method of solving systems of equations, and this one is called substitution. And the idea with this one is that you have two equations. So we have a red one and a green one here, and what we're going to do is we're going to isolate one of the variables in one of the equations and then use that information and plug that information into the other equation. Okay, so let's just get right into it. So what I'm going to do here, and this is a little tricky, it just takes some practice, is I'm going to look at my two equations and figure out if there's a variable that I can isolate relatively easily. And by isolate, I just mean get by itself. And I don't mean 2x by itself, I mean x by itself, or y by itself, or this x by itself, or this y by itself. I'm going to say that this y right here looks pretty easy to get by itself. So if we just take this equation over here, and we write 2x plus y equals 8, and we solve for y. If we get y by itself, then I'll subtract 2x from both sides. And we've got y is equal to 8 minus 2x. Okay, so this right here that I'm boxing in is telling us the exact same thing as this. It's just written differently. But what's interesting here is what I'm going to do is I'm going to use the knowledge that y is equal to 8 minus 2x, and I'm going to actually plug that in to this equation where this y is. So what I'm going to do is I'm going to come in and rewrite this second equation. So I'm going to say 5x plus 2y, and instead of y, I'm going to actually plug in what y equals. I know y is 8 minus 2x. I don't know what that is as a number, but I know that that's what y is. Okay, and I'm going to finish that equation. So we've got 5x plus 2y, where y is 8 minus 2x, because I know that, is equal to 19. And so what I've done now is I've substituted the information in about y into the second equation, and now I can solve. If you look at the equation here, it looks a little messy, but it only has one variable. It only has x in it. The problem with systems of equations like these, when you have an x and a y, is that if you have two different variables in one equation, there's not enough information to solve. You would have to have two equations to be able to solve, which we do here. All right, so let's solve this. So we're going to have 5x plus, what I'm going to do, 2 times 8 and 2 times negative 2x there. So 2 times 8 is 16, and then 2 times negative 2x is going to be negative 4x. That's going to be equal to 19. I'm going to bring that 19 down. I'm just going to collect like terms here. So I've got some x's. So organizationally, I'm going to underline those just so I can keep track of them. 5x minus 4x is just x. And then I have plus 16. And that's supposed to be equal to 19. And now we can just subtract 16 from both sides. And we're left with x is equal to 19 minus 16 is 3. And let's move that x over a little more. Okay, so that's one of my numbers. If x is equal to 3, we're not done yet. When they ask us to solve a system of equations, the goal is to find both x and y values. But here's the nice thing. If you know for sure that x is 3, you can use either equation up here. It doesn't really matter to figure out what y is. I'm going to say that we use the first equation. In fact, I would actually recommend using this right here, since we already figured out what y was in terms of x. So we'll just come down and say, great, y, we know y is 8 minus 2x. So let's just say that y is 8 minus 2 times 3, because we know x is 3. That's probably the quickest, easiest way to do it. Okay, so y must be 8 minus 2 times 3 is 6, so y must be 2. So our solution then, if we're going to write this out and be mathematically correct, our solution is actually an ordered pair. It's 3, 2. The x value is 3, and the y value is 2. That was a terrible box. Let's try that again. That's only slightly better. Okay. One thing I want you to do is I want you to check these. Okay. So let's make a copy of this. So I've copied the original equations, and what we're going to do now is we're going to plug in the values for x and y and make sure it works. So we said earlier that 2x, which in our case is 3, plus y, which in our case is 2, was supposed to be equal to 8. Okay? So the question is that actually true? Is 2 times 3 plus 2 equal to 8? It sure is. Okay, so that works. What about our green equation? We said 5 times x, which in our case is 3, plus 2 times y, which in our case was 2. This was supposed to equal 19. The question is, and I put that question mark there because I'm not saying it's equal to 19. I'm just checking to see if it's actually equal to 19. Is it equal to 19? If you do 5 times 3 plus 2 times 2, you get 15 plus 4. That is 19. So that works. So what's really nice about this is when you do this correctly, you can plug it in and make sure it works, and it does. And that way you know with 100% certainty that you are correct and you have the right solution. By the way, if you ever get a solution for a system of equations, there are 3 scenarios that could happen. You could either have no solutions, one solution, or infinite solutions. This is the case where we only have one solution. All right, let's look at another example. All right, solve the system by substitution. So sometimes we don't call it a system of equations because we're lazy. We just call it a system. But it's clear from the context that we have a system of equations. Okay, so like I told you last time, I would recommend getting a variable by itself and then substituting that information back into the other equation. This one is slightly more complicated because we don't have just a simple variable all by itself. On the last one, we had a y that was pretty easy to isolate on its own. What I'm going to recommend, let's look at this. So would it be easy to get the 4x, to get the x by itself here? Well, we'd have to add 2y, and then we would have to divide by 4. I'm a little hesitant to do that because I noticed that I have a 2y, and if I divide by 4, I'm going to get a fraction. Sometimes fractions are inevitable, but I like to avoid them if possible. What about this y? If we got the y by itself, could we do that without getting like awful fractions? So we'd have to subtract the 4x, and then we'd have, negative 2y is equal to 10 minus 4x over here, and then we could divide by negative 2. That could work. It's not the prettiest, but that could work. If you look at the blue equation, you've got 5x minus 3y is equal to 11. If we get the x by itself here, we're going to have to add 3y and divide by 5, but then we're going to get awful fractions, so I would not recommend that. And then if we try to get the y by itself here, we're going to have to subtract 5x, and then we'll have to divide by negative 3. We're going to get fractions if we do that, like really awful fractions. So I would not recommend solving anything in that first equation. Anything in that second equation. I would stick with the first equation. So let's actually roll with this first equation here. So we're going to take 4x minus 2y is equal to 10. And let's get y by itself. So if we subtract 4x from both sides, then we will have negative 2y is equal to, you can put negative 4x plus 10. Since we're not graphing anything, I'll just write 10 minus 4x. Okay, and now what we're going to want to do is we're going to want to divide everybody by negative 2. We're not subtracting 2, we're dividing by negative 2 here. So when we do that, we get y is equal to 10 divided by negative 2 is negative 5. And then negative 4x divided by negative 2 is plus 2x. Okay, so right here, it's not a solution or anything, but what this is the information from the first equation in a much more nicely packaged package here. So this is saying literally the same thing as this, but what we can do now is that we know that y is equal to negative 5 plus 2x. What we're going to do is just take it over here and drop it in the blue equation. Don't put it back into the orange equation. If you put it back into the orange equation, you're going to get something that equals itself. You'll get something to the effect of 10 is equal to 10. And you're going to be very confused. Like, I know 10 is equal to 10. All right, so let's do this. So we're going to bring this blue equation down now. So we have 5x minus 3y. And we're going to fill in the y now. The y is negative 5 plus 2x. That's the y. So 5x minus 3 times y is equal to 11. So we bring the 11 down there. Okay, and now we're just going to solve. So we're going to have 5x, and then we're going to take this negative 3 and distribute it to both parts here. This is probably the most common mistake I see in this, so make sure you don't make that mistake. All right, so negative 3 times negative 5, that's plus 15. And then negative 3 times positive 2x is going to be minus 6x. That's going to be equal to 11. And now we're just going to simplify. So, all right, 5x and negative 6x. So if you add those two together, you get negative 1x. I'm just going to write negative x. And then plus 15. That's equal to 11. And from here, let's subtract 15 from both sides. So minus 15, and what we're left with is negative x is equal to 11 minus 15 is negative 4. If you divide by negative 1 on both sides, you'll get x is equal to 4. Okay? That's one of our solutions. If x is 4, we're not done yet. A lot of my students just solve this and they're like, oh, sweet, x is 4, I'm done. Make sure you go back and figure out what the y value is as well. So you're welcome to go all the way back up to the original. Okay, so I pulled the original up there. You can use either equation. But again, what I like to do personally is if I figured out what y was in terms of x, then I'll just take the 4 and plug it in where that x is, and it'll give me the y instantly. That's kind of my preferred method if possible. So now we know y is negative 5 plus 2 times x. And instead of x, let's just put in 4 because we know x is 4. So y must be negative 5 plus 2 times 4 is 8. So y must be negative 5 plus 8 is 3. Okay, so the solution here then, if we were going to write this out, would be the x coordinate followed by the y coordinate. And don't forget to check your answers. So let me go up and copy the original and I'll bring it down. Okay, so these were the original equations. So we had 4x minus 2y was equal to 10. And 5x minus 3y was equal to 11. So let's just plug these in, make sure they work. So we're going to say that 4 times x, which in this case x is 4, and again I'm just pulling from here. This is the x value, this is the y value. Minus 2 times y, where we know y was 3, is supposedly equal to 10. Okay? So I'm putting a question mark there because I'm just double checking here. All right, so is that true? Is 4 times 4, so 16 minus 6 equal to 10? It sure is. So we're good on that one. How about the blue equation here? How about 5 times x minus 3 times y? Is that actually equal to 11? Okay, so I'm going to plug those in. X is 4, y is 3. So is it true that 5 times 4, which is 20, minus 3 times 3, which is 9, is 20 minus 9, 11? It sure is. So it works. That's exciting. I like when things work. All right, I want to look at 2 more examples with you. I promise you this is going to be the hardest one, and I just want to walk you through a hard one that has fractions because, you know, we don't live in the perfect world, so not everything works out nicely. All right, so we've got a couple equations here. We've got 2x plus 3y is equal to 7, and 4y minus 7x is equal to negative 10. And the question is, can we maybe isolate one of these variables as cleanly as possible? And the answer is not really, unfortunately. So if that's the case, well, generally what I would recommend is not solving by substitution. But in this case, it's probably our best bet to get the x by itself. Let's try that. A lot of these don't really have like a clear answer. Like I'll do a problem in class and then a student will do it differently and they do it better than me. So it's not like there's a quick, easy way to diagnose these. All right, so let's get x by itself here in this first equation. So 2x plus 3y equals 7. And we're just working to get x by itself here. So let's subtract 3y from both sides. And then we get 2x is equal to 7 minus 3y. If you want to put negative 3y plus 7, that's fine. And then from here, we're going to divide by 2 on both sides. Make sure everything gets divided by 2. And that's going to be x is equal to 7 halves minus 3 halves y. You can put 3y over 2, but I'm just going to put 3 halves y. Same thing. Okay, this is probably the best we're going to get as far as a clean fraction. Okay, so what we're going to do now is this equation is giving us the exact same information as this original green equation. And so what we're going to do is we're going to take this green information and plug it into the orange equation. Never, never, never plug this information back into this equation. Like, don't substitute for this x with this information, because you'll get basically 7 equals 7, which doesn't help at all. All right, so let's come down and copy this again. So we got 4y minus 7x. And instead of x, I'm going to put in this green information. So I got 7 halves minus 3 halves y is equal to negative 10. And there's just no nice way to do this. It's going to have fractions. So let's just bite the bullet and do it. So we got 4y. Okay, we're going to have to distribute the negative 7 here and also here. When we distribute the negative 7 with the 7 halves, remember, when you multiply a fraction, you just multiply the top with the top and the bottom with the bottom. If you have something out in front that doesn't have a bottom, it goes with the top. So this will be minus 49 over 2. So that's negative 7 times 7 halves. And then if we do negative 7 times negative 3 halves y, that will give us plus, because there's 2 negatives, 21 over 2 y. That's going to be equal to negative 10. Okay, I'm going to draw some dividers here so that we can see our work. All right, now we're here, and I personally, some people would disagree with me on this. I like to multiply everything in here by 2. I'm going to multiply the entire left side by 2, and I'm going to multiply the entire right side by 2. What that does is it gets rid of the fractions. Some people will actually work with the fractions for now and then multiply at the end, but I like to multiply just to get rid of the fractions. Okay, when you do this, make sure the 2 goes to everything in here. The 2 needs to multiply all 3 of these things in here. Okay? So when we do that, we're going to get 2 times 4y is 8y. 2 times negative 49 over 2 is actually just negative 49. Part of the reason that we're multiplying specifically by 2 is that we'll get rid of the 2 on the bottom here. It's going to do the exact same thing over here. So that's kind of convenient, actually. What's going to happen here is we're just going to end up with 21y. Because this 2 and this 2, when you have 2 over 2, it's just 1. So basically it goes away. All right. 2 times negative 10 is negative 20 over here. And then the rest isn't too bad. So let's see. We have 8y and 21y. So that's 29y minus 49 is equal to negative 20. And then we'll add 49 to both sides. And we'll get 29y is equal to negative 20 plus 49 is 29. Oh, that's actually rather convenient. Sometimes on these problems you get fraction substitutions, you get fraction answers, and it's, yeah. All right, so if you divide by 29 on both sides, you'll get y is equal to 1. So 29 over 29 is 1. So y is 1. And let's use that information now. So I'm going to go back up to this green part here. If y is 1, then we can find x fairly easily. So let's rewrite this information here. So we're going to say x is equal to 7 halves minus 3 halves y, where y is just 1. So x must be 7 halves minus 3 halves times 1 is just 3 halves. And if you have 7 halves and you're taking away 3 of those halves, then you just have 4 halves. So this is rather convenient. X works out to be 2. Okay, so our solution then, our answer, would be the ordered pair. Always put the x first, 2, 1. And if you double check these and make sure they work, let me copy that equation. I'll bring it right down. Okay, so I grabbed that equation. Let's just check these. So the first original equation was 2 times x, which happens to be 2, plus 3 times y, which happens to be 1, is supposedly equal to 7. Is that true? Is 2 times 2, which is 4, plus 3 times 1, 7? It is. How about the orange equation? 4 times y, which is 1, minus 7 times x, which is 2. Is that actually equal to negative 10? So 4 times 1 is 4, minus 7 times 2 is 14. So 4 minus 14 is negative 10. That works as well. So you know this works. And by the way, if you go back and you try to plug it in and it doesn't work, that means that you made a mistake somewhere and you're going to have to find your mistake. Unfortunately, there's not an easy way, an easy, quick way for finding your mistake. So you're just going to have to go back and rework the problem. I generally recommend, if you're having a hard time finding your mistake, just redoing the problem from the start. Like, don't look at your old work, just redo the problem from the start. A lot of times you'll catch your mistake quicker that way. All right, last example here. So solve the system by substitution. We've got 2 equations, and look at this. We've got a nice x all by itself here. So let's isolate that x by itself. So x minus 3y is equal to 3. If we add 3y to both sides, then we will have x is equal to 3 plus 3y. If you want to put 3y plus 3, that's fine. I'm just going to do 3 plus 3y. And we're going to take this information and substitute it back, not into the blue equation, which is where we got it from. We're going to substitute it back into the green equation. So let's do that. So the green equation is 3x, which x I now know is 3 plus 3y, plus 2y is equal to negative 13. So we'll distribute here. So 3 times 3 is 9. 3 times 3y is 9y. Plus 2y is equal to negative 13. And now we're just going to combine like terms here. So 9y and 2y makes 11y. Plus 9 there. That's equal to negative 13. Subtract 9. Subtract 9. And we're left with 11y must equal negative 13 minus 9 is negative 22. If you divide both sides by 11 here, divide both sides by 11, then you'll get that y must be negative 2. And we can have negative solutions. I know we haven't had one yet, and that's why I wanted to do this specific example. Okay, so, all right, y is negative 2, so don't freak out if you get a negative solution. That happens sometimes. Let's actually go back. I'm scrolling up just a hair here so that we can see what x was, and now I'm just going to use that information to find what x is. So x is supposedly equal to 3 plus 3 times y, but now I know that y is negative 2. So x is 3 plus negative 6, which is really just 3 minus 6, which is really negative 3. So x is negative 3, y is negative 2. And so our answer is negative 3, negative 2. And just for the sake of checking negative answers, I'm going to do this. If you feel good, obviously you can stop watching the video. But for the sake of those of you who want to see and make sure that it works, we'll do it. So I'm actually just going to bring you along for the ride here as I copy this down. So this is the original equation. Let's check our answer. So is x, which is negative 3, minus 3y which is negative 2, is that actually equal to 3? We might want to actually work this out. Negative 3, and then minus 3 times minus 2 is plus 6. So is that actually equal to 3? It is. That works. Okay, all right, let's try the green one now. So 3x, which we know is negative 3, plus 2y, and we know y is negative 2. That's supposedly equal to negative 13. Is it actually? So this would be negative 9, and then 2 times negative 2 is negative 4. So is negative 9 minus 4 actually equal to negative 13? It is. It works. So we're done. All right, that's how to solve a system of equations by substitution.